Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be covering topics from week 5 of Math 136. We're going to cover sections 3.1 through 3.3, which is all about functions. So let's go ahead and get started with section 3.1. The first thing we're going to do is determine if a relation is a function algebraically. So the first thing we have here is a definition. Let x and y be two non-empty sets. A function from x to y, or from x into y, is a relation that associates with each element of x exactly one element of y. So if we want to determine if a relation is a function, we need to go ahead and see if this is the case. Each element of x has exactly one element of y. So we have levels of education here and unemployment rates. So this one is going to be a function because these are going to be our x's right here, and each one corresponds with one value of y. The domain is going to be all levels of education, which include no high school diploma, some college, and college graduate. And then our y's, which is going to be our range, include the values 3.4, 5.4, 5.9, and 7.7. We write them in this order because they're ascending, which makes a little more sense. This one right here, we have these various calories for, it looks like different burgers or different types of fast food sandwiches. And then we have the grams of fat. This one is also a function. One thing you'll notice that's slightly different from the other is that the Burger King chicken sandwich and the McDonald's McChicken both go to 23 grams of fat. That is okay. The domain is going to be all of the calories of these sandwiches, 410, 430, 540, 580, 600, and 750. So we have 6 different things in our domain. The range only includes 5 different items. We only list the 23 once, even though it occurs twice. So we have 19, 23, 24, 29, and 33. It is okay for more than one element of the domain to correspond to the same element in the range. So it's fine to have 2 different x's go to one singular y. The problem comes here where we have different carats for maybe a diamond or something, and then different prices. Now this is not a function because if you look, the 0.86 carats corresponds with 2 different prices. So each element in the domain does not correspond to exactly one element in the range. It corresponds to more than one. That is not okay. So you can have a y that's used more than once, but you can't have an x that corresponds to more than one y. So that is not a function. When you don't have a function, then you don't list the domain and the range. Okay, we can also look at kind of sets of points and determine if something's a function. So for A, we have points 2, 3, 4, 1, 3, -2, and 2, -1. So one thing you might notice is you want to look for repeating values for x, okay? And if you look here, we have 2, 3, and 2, -1. So that one is not going to be a function because the element of 2 is assigned to 2 different y's. So anytime you have the same x and 2 different y's, that is not a function. All right, if we look down here, we have points -2, 3, 4, 1, 3, -2, and 2, -1. So if you look at specifically just our x's, we have -2, 4, 3, 2. None of those are repeating, so this is a function. The domain would be -2, 4, 3, and 2. We would probably want to list those in ascending order. And then the range would be 3, 1, -2, -1, again, probably in ascending order. This one, we have, didn't mean to show the answer, sorry about that. We have 4, 3, 3, 3, 4, -3, and 2, 1. Again, we have 2 x's, when x is 4, that have the same x value but different y's, 3 and -3. Now, it's not a problem. These 2 pairs right here, 4, 3, and 3, 3, this is okay that they have the same y value. That's not a problem. The problem happens when you have the same x value, this 4 and 4, with different y values, 3 and -3. So the element 4 is assigned to both 3 and -3. So that's where the issue comes up. Okay, now if we look at this equation here, y equals -1/2 x minus 3, we want to determine if that equation defines y as a function of x. So in order to do this, it's easiest if you go ahead and solve for y and then kind of look and see if you had an input for x, would it have only one output for y? And if you think about it, if you put something in for x, like 2, for example, you do -1/2 times your number, 2, and then subtract 3. That's just going to give you one output for y. So yes, that one's going to be a function. It'll be a little easier to see when you have something that's not. So let's look at this here. Determine if the equation x equals y squared plus 1 defines y as a function of x. So the previous one was already solved in terms of y. This one we want to go ahead and solve for y. That means we want to get y by itself. So if we look on the right hand side here, we have this plus 1 attached, so we need to subtract 1 from both sides. So we have y squared equals x minus 1. And we went ahead and we rearranged this so that the y squared is on the left, which is just kind of typical. And then in order to get rid of the square, you go ahead and take square root of both sides. The thing to keep in mind, this is something that students forget a lot, the thing to keep in mind is that whenever you take square root in an equation, you have to put a plus or minus out front. So what you end up with is y equals plus or minus the square root of x minus 1. Now, if you think about it, if you pick a value for x, like let's think about x equals 5. If you plug 5 in here, 5 minus 1 is 4, the square root of 4 is 2, and we have this plus or minus out front, so we get two different y values, positive 2 and negative 2, when x is 5. So this one is not going to be a function, because any value of x that's greater than 1, when you plug it in, you have two different outputs for y. So one value of x corresponds with two different y's, which makes it not a function. Okay, in this section, we also want to be able to find the value of a function. So if you think about a function like a little machine, you have an input x, it goes through this function machine, and then it outputs y. Now, one kind of typical way of writing the output is you could just say y, but a kind of more typical thing that you might see or start to see is f of x. F of x is just y. It's function notation, and it allows you to kind of do some extra things other than just putting y, which we'll see in a second. Now, a couple of things about functions. They only accept the numbers from the domain of the function. So if something's not in the domain, then we can't put it into our function. And then for each input, there's going to be exactly one output. Now, one thing to note is that those outputs can be repeated for different inputs. But anytime we input a number, like let's say we input 2, we're only going to get one output. Now, it could be true that we input two different numbers and we get the same output, and that is fine. Okay, so here are some ways that we might start to use this function notation. So for the function defined by f of x equals -3x squared plus 2x, we want to evaluate the following things. So the first thing we're going to find is f of 3. Now, if you recall, we have this f of x notation. So in order to find f of 3, or f of any number, all you have to do is take whatever's in parentheses here, in this case we have 3, and plug it in everywhere we see an x. So f of 3 is going to be -3, that's this -3 here, times 3 squared, because what we're doing is we're taking this 3, which is in red, and we're plugging it in everywhere we see an x. So we have -3 times 3 squared plus 2 times 3. Now, the thing to keep in mind, this is something that students tend to get a little confused on, is they try to do something with f of 3. F of 3 is just y, okay? That's just going to be your y value. You do not subtract 3 or divide by 3 or do anything, okay, with that left-hand side. That's just notation, okay? So all you're doing is you're simplifying the right-hand side here. So if you take 3 squared, you get 9. 9 times -3 gives you -27. -27 plus 6 gives you -21. So what that tells you is that when you put 3 into your function machine for x, you get out a -21 for y. All right, now if we have f of x plus f of 3, we already know what f of 3 is, but what we're going to do is we're going to take f of x and we're going to add whatever we got for f of 3 to it. So if you look at all of these steps, let's just pretend for a moment that we didn't already know what f of 3 is. F of x is just this right here, negative 3x squared plus 2x. So the f of x is just this portion of our equation here. And then we have a plus sign because we're adding f of 3, which is exactly what we did right up here, where we took 3 and we plugged it in for x. Now we already know that this thing right here, since we just walked through simplifying it, is negative 21. So what you get when you actually do f of x plus f of 3 is f of x, which is negative 3x squared plus 2x, plus f of 3, which is negative 21. So your final answer is negative 3x squared plus 2x minus 21. Now this one didn't have any like terms to combine, but it is always possible that you might have to combine some like terms at the end, and you would want to do that before you put your answer into MyMathLab. Okay, for part C, we want to take 3 times f of x. So since the 3 is outside, all we're doing is we're taking f of x, and we're just multiplying everything by 3. So the 3 is outside of your notation, so you just take 3 times f of x, which is just negative 3x squared plus 2x. Now anytime you have a number outside, you need to distribute it. You need to make sure you do not forget your parentheses. So we're going to take 3 and we're going to multiply it to both pieces. So we have 3 times negative 3x squared, which gives us negative 9x squared, and 3 times 2x, which gives us 6x. So 3 times f of x is just negative 9x squared plus 6x. Now, please keep in mind, we're only simplifying the right-hand side of these kind of equations. 3 times f of x is just our notation, okay? So all we're doing is we're finding this value. We're not trying to get f of x by itself or do anything like that. We're just simplifying the right-hand side. Okay, f of negative x. So what this one means is that everywhere you see an x, you're going to be replacing it with negative x. So what we have here is negative 3 from our equation up here times negative x squared, since in the place of x we're putting a negative x, plus 2 times negative x. Now we need to make this look a little nicer. Please recall that anytime you square a number, it's going to be positive. So we have negative x squared. That's just going to give us x squared. So we have negative 3 times x squared, that's this portion right here, and then minus 2x, which is going to be this right here. Okay, the next thing we're going to do from this section is finding the domain of a function. So if we have something like this, f of x equals x plus 4 divided by x squared minus 2x minus 3. At this point in the class, there are only 2 main things that you need to keep in mind with domain, and that is denominators and square roots. So eventually we're going to be doing other things like logarithms, and that will have additional domain restrictions. But for right now, the only 2 things you need to actually think about when you're asked about a domain question are, does my function have a denominator, and does my function have a square root? Okay. If it doesn't have either of those things, then for right now, your domain is going to be all real numbers. But if you do have a denominator, then you're probably going to have to exclude a number or 2. And if you have a square root, then you're going to have to exclude a lot of numbers, most likely. That's not always the case, but typically that's how it's going to work. So if we look at this example here, f of x equals x plus 4 divided by x squared minus 2x minus 3. Now hopefully you notice here we have a denominator. Denominators cause trouble because if you think for a minute, try to think about which number you're not allowed to divide by, just in general. And hopefully you came up with 0. Okay, you're never allowed to divide by 0. If you try putting in your calculator 100 divided by 0, you're going to get a domain error in your calculator. Okay, you're never allowed to divide by 0. So what we need to do is we need to figure out where is our denominator 0. So we're going to take x squared minus 2x minus 3 and set it equal to 0. Now this one is fairly nice because this is factorable. Okay, occasionally you might get equations where you have something that's not factorable, in which case you need to go ahead and use quadratic formula to find the values to exclude. But this one's going to factor into x minus 3 times x plus 1, because we're looking for something that has that multiplies to negative 3, sums to negative 2. And our two kind of solutions from this would be x equals 3 and x equals -1. Now we're talking about domain. We don't want our denominator to be 0. So what we need to do is we need to exclude the numbers that make it 0. So we write this in the set builder notation here, which starts with a curly bracket, has an x and then a line, and then x not equal to 3, because if we plug 3 in, that makes our denominator 0. And also x not equal to -1, because if we plug a -1 in, that makes our denominator 0 as well. Now, if we want to read this, we read this line as such that, okay? So we can read it as x such that x is not equal to 3 and x is not equal to -1. For this one here, though, if you look at g of x equals x squared minus 9, we don't have a square root, and we also do not have a denominator. So the domain is going to be the set of all real numbers. Anytime you don't have a denominator or a square root, you can go ahead and just say that it's all real numbers. Now this one down here, we have square root, we have h of x equals square root of 3 minus 2x. Now, if you try putting square root of a negative number in your calculator, what you'll see is that you're going to, again, get some kind of a domain error or other calculator error. We can't take square roots of negative numbers. Now, when we do a section on imaginary numbers, you will see that we will have some square roots of negatives. But for now, we don't have anything like that. So what we need to do is we need to make sure that whatever is under the square root is at least 0. Now we can take square root of 0. Square root of 0 is just 0. So what we need to do is we need to set 3 minus 2x, because that's what's under our square root, greater than or equal to 0, and then we need to go ahead and solve it. So we're looking for non-negative numbers. Those are the ones that are going to have real square roots. And if we actually solve this using some of the previous techniques we end up with x less than or equal to 3/2, or we can write it as -infinity to 3/2 with a bracket. Now let me talk about this for just a minute. So in order to solve this, we subtract 3 from both sides, divide by -2. Please recall that when you divide by a negative number with with an inequality, that you have to flip the inequality. So what we get is x less than or equal to 3/2. So this is one way to write your answer. If my MATLAB asks for it in set builder notation, then it's going to be this solution right here, where you have x such that x is less than or equal to 3/2. So if you think about it, what you're doing is you're taking all of the x's that are 3/2 and smaller. So another way to write this would be in interval notation, which I have talked about in previous online lectures. So interval notation is going to go from -infinity all the way up to 3/2, and it's going to be a bracket because we're including 3/2. So again, if you're finding domain, what you want to do is you want to either, if you have a denominator, you want to exclude the values that make the denominator 0, and then if you have a root, you want to set it greater than or equal to 0, and then go ahead and solve. So here are a couple of steps for finding the domain. The first step is to start with the set of all real numbers. If the equation has a denominator, exclude any numbers that give a 0 denominator. And then if the equation has a radical that has an even index, so square root, fourth root, sixth root, and so on, you exclude any numbers that cause the expression inside the radical to be negative. Now it is fine to have all real numbers if you have a cube root or a fifth root or something like that, because those can be negative. So you're looking for radicals that have even indexes or even indices like 2, 4, 6, and so on. Okay, next we're going to be performing algebraic operations on functions. So f and g are going to be functions. The sum f plus g is defined by the following. F plus g of x is just f of x plus g of x. The difference, f minus g, is just going to be f of x minus g of x. And then the product is going to be f of x times g of x. The quotient, f divided by g of x, is just f of x divided by g of x. And it's important to note here that g of x cannot be equal to 0. So these functions are fairly intuitive. They are kind of what you would think that they are. So let's look at a couple of functions here. Let's say we have f of x equals 2x squared plus 3 and g of x equals 4x cubed plus 1. So for this one, we want to first find f plus g of x, then we're going to find the difference, the product, and the quotient. So if we want to find f of x plus g of x, all we do is we just add everything together. 2x squared plus 3 plus 4x cubed plus 1. We want to go ahead and write it so that we have kind of a descending order of our exponents, and so that we've combined any like terms that we have. So 4x cubed is going to come first, and then plus 2x squared. 3 plus 1 gives us 4. So this would be our new function that we get when we add f of x and g of x. Now if we want to subtract, we take f of x, 2x squared plus 3, and subtract g of x, which is 4x cubed plus 1. Now the thing that's easy to forget here is that you need to make sure that you have your negative, and then you have parentheses around your entire other function. Now again, we write this in descending power order. So we get negative 4x cubed plus 2x squared plus 2, because 3 minus 1 gives us positive 2. Now if we want to multiply, we just have 2x squared plus 3 times 4x cubed plus 1. You have to use FOIL, so the first terms are going to give you 8x to the 5th. The outside term is going to give you 2x squared. The inside term is going to give you 12x cubed, and the last term is going to give you 3. It might be slightly nicer to write the 12x cubed before the 2x squared, but as long as MyMathLab doesn't state that you need it that way, it's fine to put it this way. Now f of x divided by g of x, all you do is you take your first function that's in the numerator, 2x squared plus 3, and divide it by 4x cubed plus 1, and that's it. Now if it asks you to simplify, it might be possible that you can factor f and g and then cancel some terms. So you may want to keep that in mind. Okay, now we're moving on to section 3.2, which kind of answers the question, is the relation of function determining this graphically? So we just looked at the algebraic way of determining if something is function. We're going to also determine it from a graph. So we have something called the vertical line test, which once you understand how to do it is quite easy. Basically, a set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph in at most one point. So the easiest way to do this is to actually show you guys. So what you want to do is you want to take a vertical line. Normally I suggest that students go ahead and take a pen or a pencil and just hold it vertically in your hand. Okay, so straight up and down. And then what you're going to do is you're going to take that pencil and you're going to move it across the graph. Okay, so you're going to take your pencil, which can kind of be illustrated by this dotted line here, and we move it across our graph. And what we notice is that in each place, it's only going to hit our graph one time. So for example, right here, it only hits our graph once, here once, and so on, all the way across. So that means that yes, this is a function. This is the graph of the equation y equals x squared. Now if we do the same thing over here, again, we have our vertical line, we move it across, it only hits once in each of the places. This is y equals x cubed. Both of these are actually functions. If we take a look at some that look like this though, this is a sideways parabola. So we take our vertical line and we move it across, and what we notice right away is that our vertical line hits our graph in two different places. In this case, it hits at 1, 1, and 1, -1. This automatically means that this automatically means that this graph is not a function. Okay, and if you look at the equation, we have x equals y squared. If you remember how we did this algebraically, we solved for y. And if you think about solving for y, we would end up with y equals plus or minus the square root of x. That's going to give us two different outputs for each input of x, which causes a problem and makes this not a function. In addition, down here we have the equation of a circle. It's going to be the same kind of thing. When we take square root, we get plus or minus. You'll notice that when we move our vertical line through, we hit in 2 points, kind of all the way across our circle. So these are also not functions. Okay, in section 3.2, we're also going to learn how to obtain information from the graph of a function. So if we look at this graph here, we have kind of a whole set of points here. This is looks like some kind of sine or cosine curve that you don't need to really worry about. This is going to be used to kind of demonstrate how we obtain information from a graph. So for example, the first question is what are f of 0, f of 3 halves, and f of 3 pi over 2 and f of 3 pi. And what we're doing is we're just looking at our x values because it's always f of x. So we take whatever's in this parenthesis and that's going to be our x value. So at x equals 0, we're looking right here. We get 4 out for y. That's right there. So f of 0 is just 4. And then f of 3 halves, sorry, this is not given, but if we look over at f of 3 halves, or 3, geez, I cannot say this right now, f of 3 pi over 2, what we would do is we'd look over at 3 pi over 2, and we'd notice that our y value is 0 there. And then if we look at f of 3 pi, if we go over to 3 pi, which is right here, we get negative 4 out for y. So that would be f of 3 pi over 2 and f of 3 pi. It would be 0 and then negative 4. Now question B, what is the domain of f? So domain is all x values. So we start on the left, we find our smallest x value, and we move over to the right until where we get our largest x value. And that's going to be from 0, including 0. So we have a parenthesis there because there's an actual dot there, all the way over to 4 pi. So there are two ways to write this. Interval notation would be 0, 4 pi, both with brackets since they're included. Or if you wanted set builder notation, it would be x such that x is between 0 and 4 pi inclusive. Range, we're going to be looking up and down. We find our smallest y value by starting at the bottom and moving up. And you'll notice that the smallest y value that we have is negative 4, and then the largest y value that we have is positive 4. So our range is, in set builder notation, going to be y such that y is between negative 4 and 4 inclusive, or we could write it in interval notation from negative 4 to 4, both with brackets, since negative 4 and 4 are both included. If we want to list the intercepts, that means we're trying to find our x-intercepts and our y-intercepts. We have one at 0, 4. We have one at pi over 2, 0. So this first one's a y-intercept. This next one's an x-intercept. We have another x-intercept at 3 pi over 2, 0. Another x-intercept at 5 pi over 2, 0. And a fourth x-intercept at 7 pi over 2, 0. You need to make sure that you pay close attention to these instructions in my math lab. It's really easy to get points marked off just for silly mistakes. What you want to do with these is you want to make sure that you put all of the intercepts in their own parentheses and then put commas between each. Another question we could answer is how often does the line y equals 2 intersect the graph? So if you think about the line y equals 2, it's going to be this purple line here. And if you look at how many times it intersects our graph, it intersects it in 1, 2, 3, 4 different places. And then for what values of x does f of x equal negative 4? And if you look at that, it's going to be these two red dots right here. So that would be at x equals pi and x equals 3 pi. And then for what values of x is f of x greater than 0? So if you look greater than 0, that means y is greater than 0. So what we're looking for is this piece right here, which goes from 0 to pi over 2, because this is above our x-axis, so they're positive y values. And then from 3 pi over 2 all the way over to 5 pi over 2, because these are all positive. And then from 7 pi over 2 all the way to 4 pi. Now you'll notice that the 0 and the 4 pi are included because at 0 and 4 pi we have values of 4, which are greater than 0. But these endpoints here of pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2 are not included. Excuse me. Because at those x values, we just have y equals 0. Now, we want f of x greater than 0, not greater than or equal to 0. If we wanted greater than or equal to 0, then we would have had brackets everywhere. Okay, let's look at this graph, or this function here, f of x equals x over x plus 1. Let's try to answer the question, is the point 1, 1/2 on the graph? So what we need to do is we need to plug 1 in for x and figure out what our y is. So if we plug 1 in for x, we get 1 over 2. So yes, that means that the point 1, 1 over 2 is on the graph. Then it says, if x equals 2, what is f of x? So what we would need to do is we need to plug 2 in for x. So we get 2 over 3. So the point on the graph is going to be 2, 2/3. If f of x equals 2, what is x? What point is on the graph? So in this case, what we're doing is we're saying f of x is 2. So we need to plug 2 in on the left-hand side. So we have 2 equals x over x plus 1. And then we go ahead and we just solve this by multiplying both sides by x plus 1. So we have 2 times x plus 1 equals x. Distribute, 2x plus 2 equals x. And get everything on the same side, solve for x. So we get x equals -2. So the point on the graph is x equals -2, y equals 2. So this is just an additional way to find out some information from a given equation. You can answer questions like, is the point on the graph? What would the point be on the graph? Without actually having the graph and just by solving it algebraically. Okay, now section 3.3 talks about even and odd functions. We can determine even and odd functions from a graph, and we're also going to do it other ways. But let's go ahead and start with the definition of even and then of odd. So a function f is even if for every number x in its domain, the number -x is also in the domain, and f of -x is the same as f of x. So even means that f of -x is equal to f of x. For an even function, for every point xy on the graph, -xy is also on the graph. Now, if a function is odd, it means that for every number x in its domain, the number -x is again also in the domain. But in this case, f of -x is equal to -f of x. And another way of saying this is that if you have the point x, y on your graph, -x, -y is also on the graph. Now here's a theorem. A function is even if and only if its graph is symmetric with respect to the y-axis, and then a function is odd if and only if its graph is symmetric with respect to the origin. So even goes with y-axis symmetry, odd goes with origin. This should be pretty easy to remember because odd and origin both start with O's, and even and y, those are both vowels, okay? So you'll remember that we don't have a special name for x if you remember those two things. So if you look at these graphs here, this first one right here is definitely symmetric with respect to the y-axis. Okay, so if we take a dotted line through our y-axis and we flip this blue across, it's going to be the same on both sides. So that's even because it's symmetric with respect to y. Now if we look at this one, this is neither. So if it's symmetric with respect to y, it means we'd be able to take this right-hand side, flip it across, and get an equivalent piece on the other side, which is not the case. Now if we took this piece and we flipped it across y and x, we still would not have this piece here because of the fact that it's been shifted from the origin. Okay, so this is not symmetric with respect to the y-axis or the origin, so it's neither even nor odd. Now this one right here, if we take this right-hand side and we flip it across our y-axis and our x-axis, we end up with this piece down here. So this is an odd function because it's symmetric with respect to the origin. Now we can also determine this algebraically. So we want to determine if the following functions are even or odd or neither, and then determine whether that means that the graph is symmetric with respect to the y-axis, the origin, or again, neither. So we have f of x equals x cubed plus 5x. So the first thing you want to do is go ahead and take x and replace it with -x. And if we do this, we get -x cubed minus 5x. Now if this is the same as your original equation, then that means that you have something that is even, meaning that it's symmetric with respect to the y-axis. But if you take this and you make the whole thing negative, so we have the negative of -x cubed minus 5x, and this is the same as your original, then it means that it's symmetric with respect to the origin. So if you take the original and you make it negative, you end up with the exact same thing here, which is just -f of x. So we always start by replacing x with -x, If that works, if it makes it the same as the original, then it's even. If it makes it the same as the negative original, then it's odd. And if neither of those things happen, then it's neither. So this one is an odd function because it's symmetric with respect to the origin. So if we replace x with negative x and f of x with negative f of x, we get something that's true. Now this one here, g of x equals 2x squared minus 3. So what we do first is we find g of negative x. So I plug it in. I have 2 times negative x squared minus 3. And if you simplify this, you get 2x squared minus 3. This is the same as my original. So that means that I have something that's even. Okay, so you plug negative x in. If it's the same as the original, then it's even. If it's the same as the opposite of the original, then it's odd. Now if we look at this one down here, I'm taking negative x and I'm plugging it in. So I have negative 4 times negative x cubed plus 1. If I simplify that, I get 4x cubed plus 1. This is not the same as the original. And if I look at the negative version of this, I would get negative 4x cubed minus 1. That is also not the same as the original. Since h of x nor negative h of x is not equal to this, the function is neither even nor odd. So that means it's not symmetric with respect to the y-axis or to the origin. Okay, we can also determine where a function is increasing, decreasing, or constant based on its graph. So if we look at this right here, we want to know where the function is increasing. So you always want to read a graph from left to right. So if you look at increasing, it's going to be increasing kind of along this red line because it's going up. So we say that it's actually increasing from negative 4 until 0. Now, when we give the increasing values, we always give the x values. So it starts increasing at x equals negative 4 and continues to increase until x equals 0. Also, the other thing you want to note is that when you give increasing, decreasing, and constant intervals, you never include the numbers. So you never use less than or equal to, greater than or equal to, or brackets. You're always using parentheses or less than or greater than. Another way to write this would be from negative 4 to 0 with parentheses. Now, where's the function decreasing? So if we look at this, it's going to be decreasing on this little piece here, and then which is from negative 6 to 4. So we look at our x values, negative 6 to negative 4. And then it's also decreasing over here, which starts at x equals 3 and continues till x equals 6. So it's from negative 6 to negative 4 and 3 to 6. Now, where is it constant? You're looking for a flat part of your graph, and that's just going to exist right here. And that's from x equals 0 all the way to x equals 3. So your interval is going to be from 0 to 3. A function f is increasing on an open interval I if for any choice of x1 and x2 within your interval I, with x1 less than x2, f of x1 has to be less than f of x2. Now we have a similar kind of definition for decreasing. A function f is decreasing on an open interval I if for any choice x1 and x2, where x1 is less than x2, so it starts the same way, we have f of x1 is greater than f of x2. And then constant would be where they're equal. So if you look at these little sketches here, you can clearly see that x1 is smaller than x2 in all of these cases, but for this one, f of x1 is smaller than f of x2, so this is increasing. For this one, f of x1 is larger than f of x2, so this one is decreasing. And for this one, f of x1 is equal to f of x2, so that means that it's constant. Now we have some properties of functions like local maxima and local minima. So if you look here, we have an example of a local maximum. So the local maximum is f of c, it's the y value, and it occurs at x equals c. And it happens when we go from increasing to decreasing. We also have local minimum. The local minimum in this case is f of c, and it occurs at x equals c as well, and it happens when we go from decreasing to increasing. So a function f has a local maximum at c if there is an open interval I that contains c such that for all x not equal to c in your interval I, f of x is less than or equal to f of c. And then the same is true, but it's a local maximum, and that's where we have f of x greater than or equal to f of c. Now, these are easiest to just kind of get used to noticing instead of actually using this definition. It's a little confusing. But if we look down here at what numbers, if any, does f have a local maximum? So what we're looking for is we're looking for kind of a peak in our graph. And if we look at it, this point right here is a peak because everywhere around it is smaller. So that means that there is a local maximum when x equals 1, and the actual local maximum value is going to be 2. So the maximum and minimum happen at an x value, but the actual value of it is the y value. Now, at what numbers, if any, does f have a local minimum? So if we look here, there's a local minimum in two places. X equals -1 because we have a dip here, and x equals 3 because we have a dip here. So there's a local minimum when x equals -1 and when x equals 3. The actual minimum values are going to be 1, that's our y value, and 0, that's our y value here. So again, the local minimum happens at an x, but the actual value is a y value. We also have something called absolute minimum and absolute maximum. And that means that it is the absolute highest or absolute lowest point on a graph. Now, it's not always something that exists. So if we look at this example here, if we look and find the absolute maximum, that's going to be the highest point on our graph. That's right here. The absolute maximum of 6 occurs when x equals 3. Now the minimum is going to be this green point down here because that's our lowest point. The absolute minimum of 1 occurs when x equals 0. Now if we look at something like this here, we have a maximum. The absolute maximum of 3 occurs when x equals 5. But if we look for a minimum, we don't have a minimum here because we have a hole, okay? So this would be our lowest point if it were included, but we don't actually have a lowest point because we can get really, really close to 3. That would be our lowest point, something right around here, but it never actually reaches 3 because we have a hole there. So there is no absolute minimum in this case. If we look at something like this, absolute maximum of 4 happens at x equals 5. And then we also have an absolute minimum of 1, which occurs on an interval from 1 to 2. So on the interval where x equals 1 all the way to x equals 2, we have a minimum value of 1. Now if we have something like this, there's no absolute maximum because if we look for the highest point, what we notice is that we have an arrow just kind of going in this direction. This means that it's going to increase forever. Okay, so there is no maximum value. It's going to go to infinity. But we do have a minimum value. The absolute minimum of 0 occurs when x equals 0. And if we have something like this, what you'll notice again is that if we look at this kind of up arrow, there is no absolute maximum because this goes up to infinity. And there is no absolute minimum here either because we have a hole at this kind of valley point that would normally be our minimum. Okay, the last thing that we're doing is rate of change, okay, average rate of change, and we have a nice little formula here. So if a and b, a not equal to b, are in the domain of a function y equals f of x, then the average rate of change of f from a to b is defined as follows. You take the change in y and divide it by the change in x, and what this really means is that we take f of b minus f of a and divide by b minus a, where a is not equal to b. Now, this might look familiar, hopefully it does. This is actually just your slope formula, okay? So we have the formula kind of written on the bottom right over here, and we want to find the average rate of change of f of x equals 3x squared from 1 to 3. So one thing we could do is we could look at our graph, and we could kind of see we're going to have f of 3 minus f of 1 over 3 minus 1. Now the order that you subtract in does not actually matter as long as you're consistent. So we've picked 3 as our first point and 1 as our second point. So we do f of 3 minus f of 1 over 3 minus 1. And if we look at our graph here, we can see that f of 3 is going to be 27, f of 1 is going to be 3. So f of 3 is just 27 minus f of 1, which is just 3, divided by 3 minus 1. So we get 24 over 2, which is just 12. Now let's find the average rate of change from 1 to 5. So what we're going to do is we're going to take f of 5 minus f of 1 over 5 minus 1. Now f of 5, that's the value that you get when you plug 5 in for x. You should get 75 for that one. So if I plug 5 into my original equation, 5 squared is 25, 25 times 3 is 75, that's this value here. So I have 75 minus 3 over 5 minus 1, which is 72 over 4, which is 18. And if we look at it from 1 to 7, we're going to notice that this is increasing even more, because really what we're doing is we're creating a line from this point to this point, and we're finding the slope of that line. Okay, here we had from these 2 points, the slope is not very steep. From these 2 points, the slope is a little steeper, and from these two, the slope is quite steep. So we have f of 7 minus f of 1 over 7 minus 1. So we get 147 when we plug 7 into the original equation, minus 3 over 7 minus 1. So we get 144 divided by 6, which gives us 24. So that means that if we were to draw a line from 13 to 747, the slope between those 2 points would be 24 over 1, or just 24.